Okay, we are looking at statics of rigid bodies, and let us start with cross product. So cross product, traditionally we have learned cross product to be vector u cross vector v is magnitude of u times magnitude of v times sine theta k cap, where sine theta is the angle between vector u and vector v, and k cap is the unit vector perpendicular to both u and v. Okay, so if you have u and v, your k cap is perpendicular to both u and v. Okay, something like that. Okay, k cap is perpendicular to both u and v cap. Okay. So cross product always follows right hand rule, right? Right. Now if your vector u is like that and your vector v is like this, you put your fingers of the right hand towards u and curl the fingers towards v, right, and then your thumb points towards the k cap. Your thumb will be pointing towards the k cap. If your u is like this, v is like this, then you have to use your right hand. This will be, your k will be downwards. Right-handed orthogonal unit vector triad. Okay, right-handed orthogonal unit vector triad. Let us look at our I, j and k axis. Okay, this is your x-axis, y-axis and z-axis. So our unit vector I cap, unit vector j cap, unit vector k cap. Now I cap cross j cap is k cap, right? We put your fingers towards x-axis and curl them towards y-axis, you get a vector along z-axis. Okay, same, j cap cross k cap is I cap, and k cap cross I cap is j cap. Now j cap cross I cap is minus k cap. So your thumb, if you are starting from j and going towards I, your thumb will be pointing towards negative z-axis, so your result will be minus k cap. And k cap cross j cap is minus I cap, and I cap cross k cap is minus j cap. Okay. You also have I cross I, j cross j, k cross k equals to 0. Because angle between them is 0, so sine 0, 0, right? Okay. So now if you have two vectors, right? Let's say we have A is A1 I cap plus A2 j cap plus A3 k cap, and you have B is B1 I cap plus B2 j cap plus B3 k cap. Now if you do A cross B, each of the terms you do cross product, what you get is okay, let's write it. A1 I cap plus A2 j cap plus A3 k cap cross B1 I cap plus B2 j cap plus B3 k cap. Okay, if we do this, you get I cross I is 0, I cross j is k, and I cross k is minus j. So if you do the whole thing, and you will get A2 B3 minus B2 A3 I cap plus A3 B1 minus B3 A1 j cap plus A1 B2 minus B1 A2 k cap. This is so basically A cross B can be written as the determinant I j k A1 A2 A3 B1 B2 B3. So here you have A should be the first, the second row, and the second vector should be the third row. So A cross B is this, right? If you are writing B cross A, you get B2 B3 A1 A2 A3. So here you have first will go there, second will go there. Okay, don't get confused. Okay. We'll look at now moment of a force, right? Of a force. Let's say you have your xy axis. There's a point A, ax, ay are the coordinates, and there is a force vector F acting at an angle of theta and you also know coordinates of point bx, by. Now you are required to find moment of force F about point A, which is same as saying about z-axis passing through A. So this is a planar problem, right? Okay. So now how do you go about doing it? You know the force and you know the angle of the force with x-axis. You can take, so this is your A and this is your B and this is your F sine theta, this is your F cos theta. Now this height, moment arm when you're calculating, okay, so you have your A and B. Okay. So this is, let's call this H, this is length L. So when you are computing moments about a point, moment about point A, you have your force F sine theta acting at a distance of L. Your R moment is R times F, right? So F sine theta times L, and this force is causing a counterclockwise moment, right? Okay, counterclockwise, plus you have F cos theta also causing counterclockwise moment, F cos theta times H, right? So this is your L is by minus ay times F sine theta, and your H is L is bx minus ax f sine theta and ay minus by f cos theta. So this is one way of doing it. You can resolve the force along x and along y, and then you can write the moment. Another way of doing it is you find the perpendicular distance, because moment of a force is about a point is force times the perpendicular distance between the line of action of the force and the axis about which you are taking the moment. So there is no such thing as moment about a point. So when in books or in anywhere when somebody says moment about a point, what they mean is moment about an axis passing through that point. Okay. So here you have, let's say, this is point B. Okay, so now you know the angle, made by this line with positive x-axis, and then you also have your H and L is also known. So now we have A and B. This is B, this is A. You have H and L, also known, theta. AX, AX, AY, BX, BY are known. So H and L are known. You also know theta and F, right? You need to find moment of F about A. Okay, so now we are trying to do it by finding the perpendicular distance from point A to the line of action of the force F, which is this, right? Okay, so we know the theta, we know H and L. So let's say we know phi equals to tan inverse of H by L. So this is phi, and this is your theta. So your remaining angle alpha is 180 minus theta plus phi. So once you know alpha, you can do sine alpha is P by AB. So your distance, perpendicular distance P is AB sine alpha. So now your moment is F times P, magnitude of F times P, and so you do this and find the perpendicular distance. This 20 Newton force acting at an angle of 60 degrees, and point B, this is point A, this is 800 mm, this is 200 mm. You want to find moment of 20 Newton force about A. So now you extend the line like that and drop a perpendicular onto that line. So now your moment arm is AC. This is a right angle triangle. So AB is 800 plus 200 square which is 824.6 mm, and this angle is theta. Let's see. Theta is tan inverse 200 by 800. This is 14 degrees. This angle here is 60 degrees. Okay. So this is also 60 degrees. So your angle ABC is 60 plus 14, 74 degrees. Sine 74 degree is AC by AB. AC is 824.6 times sine 74, this 792.7 mm. So your moment is 20 newtons times AC 15.85 Newton meter. Using matrix equations, this is A, this is B, and you have your force F and your theta, right? Okay. So unit vector will define a unit vector u cap along the line of action of the force, which will be cos theta, sin theta, and then unit vector perpendicular to F is K cross u cap. This will be, this is cos theta I cap, sin theta j cap, right? This is here I cap plus sin theta j cap. We are just writing in vector notation or column vector notation. So if you do K cross u, which is K cross I cos theta, which is K cross I will be j so this will be cos theta, this will be minus sin theta. Okay, so this is called, let's call this V cap. Okay, so now this is, we said L and H. Okay, so now vector from B to A is minus L H, right? Minus L I direction, H in J direction. This should be equal to some m units along u cap. So if you want to go from B to A, you travel minus L along I and H along J, or you travel some u units along u, sorry, m units along u and n units along B. So this is m cos theta sine theta plus n minus sine theta cos theta. This will be simply cos theta minus sine theta, cos theta, m and n. Okay. This is minus L and H. So if you do inverse, you can solve for m and n. This will be cos theta, sine theta, minus sine theta and cos theta times minus L and H. Simply multiply, you know the L, you know the H, so multiply and get n. Once you have n, your moment will be simply your F times n. Again, this direction, because about A, it is causing a counterclockwise moment. Okay. A body in 3D space. We have X, Y, Z, and then there is a body like that, and there is a force acting, let's say, in some direction, F, on the body, along that line. Okay. And you want to get the, so this is your point B and your point A is there. Now we want to get the moment of the force about point A. In this case, this is a force vector. Here you write moment is R cross F. So in case of 2D, you can write, when your problem is a planar problem, you can write moment as moment arm times the force, where moment arm and force are perpendicular to each other. Your moment arm is a perpendicular distance from the line of action of the force, perpendicular distance from the point or axis about which you want to take the moment to the line of action of the force. Okay. So here in 3D case, you have to write this as R cross F. Okay. Let's say there is a force here which has all three components, X, Y, and Z. So you have Fx, Fy, Fz acting Y and Z. So moment of force about x-axis. You want to look at moment of force about x-axis. So we will draw only the, so if you look at, so now your x-axis is coming out of the plane of the paper, and then you have Z. So your moment about x-axis is y times Fz, right? So this is the y distance this is your z distance. Y times fz about the origin, right? Or about the x-axis is y times fz, which is causing positive moment because your thumb is now pointing towards right hand rule. Again, here also right hand rule, your thumb is now pointing upwards out of the plane of the paper for y times z, and then minus because your Fy is causing a clockwise movement about the origin. Okay. Times I cap. Right? Similarly, for your y-axis, if your moment about y-axis. So if you draw this is z, this is x, and then you have fx and fz. In this case, you have moment about y-axis is let me leave some space here. Moment about y-axis is minus x fz plus z fx. J cap, right? So this is your x and this is your z. So about your y-axis, which is now in this figure, your y-axis is coming out of the plane of the paper. Now about the y-axis, your force Fz is causing a negative clockwise moment and force Fx is causing a positive moment. Finally, if you look at fx, fy, and this is distance x and this is distance y, moment about z-axis is x fy causing counterclockwise or positive moment and y fx about the z-axis, right? This is the moment about z-axis. If you add them all up, so moment of about origin is moment about x axis, moment about y axis, moment about z axis, which is, you add all the terms, this will end up being I, j, k, x, y, z, and fx, fy, fz, which is nothing but R cross F. Okay. So your moment vector also, just like any other vector, also has three components, x, y, z components, and it's also a vector. So if you look at any moment vector, after you do R cross F, so that is your moment vector, right? About x, y, z, there are three components. This is a moment vector. So we want to know moment of a force about a axis D, and let's say axis D is like that, right? And our moment vector is, so we know the R cross F, so we have computed, let's say the moment M, R cross F, and then we got the moment here, this. So now you want to know, you know the moment, and you want to know what is the moment of the force about an axis D. This moment is moment of the force about x-axis, y-axis, and z-axis, right? Now we want to know what is the moment about another axis D. How do we get that? Simply moment moment M about T is R cross F dot product with D cap. Take a unit vector along D and do a dot product. So this will end up being, instead of ijk, you have dx, dy, dz, and rx, ry, rz, and fx, fy, and fz. This will be a scalar value. Basically, you are getting components of mx, my, mz along d cap. Where here equals to cap, a cap, and d. Yeah, so this is dx, dy, dz. So this is how you find moment of a force about a given axis, if both the moment vector and the axis are both passing through the origin. What if they are not passing through the origin? What if we have this is C, this is B, and this is A. and this is the force F. Okay. Now moment of a force F about an axis along line BC. This moment is BA cross F times BC cap. Earlier we had found moment of the force about the origin. Now since we need moment of the force about an axis along BC, and BC is not passing through the origin, what we need to do, we need to find first moment of the force about the point B. So you will get moment mx, my, mz will be the axis Cartesian coordinates at B. So BA will be your R cross F, and then you get a unit vector along BC, right? So BC cap, this will be the moment of the force about an axis along BC. Okay, moment of a couple. So what is a couple? Couple is two forces, equal and opposite, acting on a body with some distance between them. So let's say two forces, equal and opposite. So you have force F acting like this, force minus F acting like this. This is acting at point B of a body. This is acting at point A of a body. So now you have X, Y and Z axis. Your RB is OB vector from O to B, that is your RB. RA is vector from O to A, that is RA. Moment of both the forces is RB cross minus F plus RA, moment about the origin, right, cross F. So your final moment is RA minus RB cross F. So you have O, A, B. B, this is A, this is O, RB and RE. Now this vector will be RB plus this vector is RA. So this vector is going to be RA minus RB. That is, let's call it that. That will be your F. This is moment of a couple. The difference between moment of a force and moment of a couple is moment of a force, it matters where your R is starting from, right? So here moment of force F, only the force F is RA cross, moment of force F is RA cross F, right? So your point O matters. You take moment about O, then it is RA cross F. If you take moment about some other point C here, then it is CA RCA cross F, right? That's how it is. But if you are taking moment of the couple, meaning both the forces together, it doesn't matter which point you are taking the moment from. Moment of a couple is independent of that. It is only dependent on the distance between these two forces. So this R, the R between A and B. To be more precise, it is dependent on only the perpendicular distance between these two lines of action, two parallel lines of action of force. Equivalence of a force at a distance R to a force and a couple at O. So let's say we have a body where you have a force F acting at a distance R from origin O. Now I will apply the same force along this parallel line here and here. So this force, this system is now equivalent to the earlier system. So when these forces were not there, sum of all the forces is only one force, F. Total force acting on the body is F, and total moment about the origin is R cross F. Total force acting on the body is F, moment is R cross F. After adding these two forces also it's still the same, right? Okay, so now I will replace these two forces, this and this, with a couple. So now same system, I have one force F and I will replace this with a moment, right? Moment of the couple, right? Okay, this is F acting here and moment acting here. So I have simply successfully moved the force from this point A to origin O. Now earlier it was only a single body where a force is acting at point A. Now we have the same body with force and a moment both acting at O. These are equivalent systems. Let's say we have this body where you have a 60 Newton force acting over there and 50 Newton force acting over there and 20 Newton force acting at an angle of 40 degrees and a couple of 30 Newton meter acting on the body. Now let's say that height is 0.4 meters. This height is 0.5 meters. This is 1 meter and this is 0.6 meters and this height is 0.2 meters. Okay. So now a total we have one force, two force, second force, third force, and we have a couple. There are a total of 3 forces and a couple acting on the system. Now find equivalent system of force couple. So replace all the forces acting at A. Let's say we want to move all the forces to point A. Now if we move, first let us look at what is sigma fx here. It is 50 minus 60 minus 20 cos 40 degrees. Sigma fy is 20 sin 40 degrees. And moments about A is minus 30 minus 50 times 0.2. Minus 30 is this, it's going clockwise, so it is minus, and minus 50 times about point A, so it is causing negative moment, plus 60 times 0.5 height and plus 20 cos 40 degree times 0.4 momentum vertical distance minus minus 20 sin 40 degree times 0.6. So this will end up being minus 11.6 Newton meter. This is $12.9 Newton and this is minus 25.3 Newton. Okay. So we will do one by one. Let us first move the 60 Newton force. If we move the 60 Newton force here, so you have 60 Newton force here and then the moment due to that force, right? So you have 60 times 0.5, so which is 30 Newton meter. It is the moment of a couple, so it can be moved anywhere, right? So you already have a 30 Newton meter already. This is there, and you have 30 Newton meter because of this. Okay, and then 50 times 0.2. So this is 60 Newton acting at 0.5 from A. So this will give you 30 Newton meter. Okay, next one we have 50 Newton from A. It is acting at 0.2 meter. So this will give counterclockwise 10 Newton meter. So here you have additional 10 Newton meter. Okay. Similarly, if you take 20 sine 40 degree, from A it is acting at a distance of perpendicular distance of 0.6. So 20 sine 40 into 0.6. This will be 20 sine 40 into 0.6. This will be 7.7 Newton meter, and it is clockwise. So you have plus 7.7 Newton meter. Okay, you can put it anywhere, doesn't matter. And then the final one, you have 20 cos is acting like that, right? 20 cos 40 degrees. It is acting at a height of 0.4. So 20 cos 40 degree times 0.4. This is 6.13 Newton meter. This is counterclockwise. You have 6.13 Newton meter. Now you should have moved all the forces here. So 20 here, and then 60 plus 20 cos 40 degree, and here you have 50 Newton acting like that, and your 20 sine 40 degree. So all the forces, 50 Newton force moved here, 60 Newton force moved here, 20 cos 40 also moved here, and 20 sine 40 also moved here. Let us copy this. So now these two are equivalent, right? So the total moment what we computed earlier for this system, Fx is minus 25.3 newtons, Fy is 12.9 newtons, moment about A is minus 11.6 newtons. Now let us look at what is the total force here. Fx is 60 minus 50 minus 60 plus 20 cos 40 degree. This will end up being same as minus 25.3 newtons, and Fy is 20 sine 40 degree, which is 12.9 newtons. Moment about A is 30 minus 30 minus 10 minus 7.7, 11.57 Newton meter. The final system is 11.6 Newton meter, and you have a force F acting there. That is so you have .6 Newton meter, and then you have .9 and 25.3. So your tan theta is 12.9 divided by 25.3. So your theta will turn out to be 27 degrees. And your resultant R is 25.3 square plus 12.9 square. This will be 28.4 newtons. So here you have 28.4 newtons acting at an angle of 27 degrees. Now we can reduce this further to a single resultant force. Acting on the body. Okay. So now if you want to have the same system and you want to have a single resultant force, let's say along OE at some point on the line OE. If you want the single resultant force, which is to replace this 28.4 newtons force at 27 degrees, this force and the moment both, then that force, that single force should cause this moment, right? So that force can be, if you are going to move along OA at some point, the horizontal component does not contribute to this. So if you, let's say we want some point there, we want to move this force to that point here, right? Only the vertical component will cause the moment. So let's say 28.4 sine 27 degrees times some x is equals to 11.6. This x will turn out to be 0.9 meters. So if you replace that force and moment by (28.4) Newton force acting at 27 degrees, then your moment about A will be, your sigma fx will be the same, 25.3, sigma fy will be the same, 12.9, and moments about A will be the same as 11.6 Newton meter. So this is how you can reduce a system which has multiple forces acting on it to a single force. Equilibrium of rigid bodies. Equilibrium. Just like points, here also you have sum of all the forces equals to 0. So sigma fx equals to 0, sigma fy equals to 0, sigma fz equals to 0. You also have, in case of bodies, sum of all the moments equal to 0. Okay. So let's say you have one single body and there are two forces acting on it. There is force 1 and there is force 2. Now, and the body is in equilibrium. Body is in equilibrium. So sum of all the forces should be equal to 0. So F1 plus F2 should be equal to 0. What this means is, if there is a body on which there are only two forces acting, then both the forces should be equal and opposite. Equal in magnitude, opposite in direction. So this is not possible. You should have equal and opposite. You also have the moment equation. So moment is, let's say if you take moments about this point A, moment about A. So you have R cross F2. R cannot be 0 because there is a finite distance between A and B, and F2. If F2 is 0, then there is no forces acting. Both F1 and F2 should be 0. So then F2 also cannot be equal to 0. So what is remaining? The angle between the vectors R and F should be 0. Only then you have R F2 sine theta. So this has to be 0, meaning both the force vector should be along the line joining A and B. So these forces should be like this. F2 and F1. Yes, this is the body. AB. Then if there are only two forces acting on the body, then both of them should be equal and opposite, and the line of action of the forces should be along both the points A and B. This is what is called a two-force member.